In this video, we are going to be looking at covalent bonding. So first, I'm going to start with the definition of covalent bonding. So covalent bonding is the strong electrostatic attraction between a shared pair of electrons and the nuclei of the bonded atoms. Okay, and examples of molecules that have covalent bonding are non-metals. So it'll always be between non-metals. So for example, if we have an element like H2, O2, so these are diatomic molecules. Within these molecules, we have covalent bonding, okay? We also find covalent bonding in non-metal compounds. So for example, H2O, so hydrogen and oxygen, both non-metals over here. So within our water molecule, we have covalent bonding. Also stuff like methane. So again, two non-metals in that one. Within the molecule, we have covalent bonding. Another example can be NH3, which is our ammonia molecule. So again, within that molecule, we have covalent bonding. We also have covalent bonding within polyatomic ions. So by polyatomic ions, I mean, so for example, ammonium, carbonate, sulfate, and so on. Okay, so these are they are ions themselves. Okay, so for example, carbonate with, for example, magnesium 2+, between these two ions you will have ionic bonding because they're ions, they're oppositely charged ions, but within this carbonate ion we have covalent bonding. So the carbon is covalently bonded to the other three oxygens. Okay, so within polyatomic ions, we have covalent bonding. And these covalent bonds are essentially formed by orbitals overlapping. Because remember, we're sharing a pair of electrons. So in order for electrons to be shared, because electrons are found in orbitals, those orbitals must overlap. So if we just choose H2, for example, in hydrogen, we just have one electron, so it's just one s1, so we just have an s orbital. In H2, those s orbitals will overlap to form the covalent bond. Okay, so those two electrons can now be found anywhere where those two s orbitals have overlapped. So they can be found anywhere in this electron cloud over here. Right, let's now have a look at dot and cross diagrams. So we've looked at dot and cross diagrams for ionic compounds. In ionic compounds, those electrons are being transferred, so we form ions, whereas in covalent bonds, electrons are being shared. So you've got to have an overlap of those shells when you're drawing the dot and cross diagram. So for hydrogen, we just have one electron in the first shell. I'm going to show that with a cross on this hydrogen, and in the other hydrogen I'm going to show that with a dot. Okay, even though we've used a different kind of notation for the electrons here, they are still exactly the same. All it does is it shows us which atom that electron was from. So when they overlap, the way that we draw it is by drawing the two shells overlapping, and the dot and the cross are being shared over here. So now we've got a shared pair of electrons. This is one covalent bond between the hydrogen atoms, and we can show that. So this is the dot and cross diagram. We can also show that as the displayed formula, and in the displayed formula we just use a line to show one covalent bond. So that's showing there's a covalent bond between this hydrogen atom and this hydrogen atom over here. So this is the displayed formula. It's also worth noting in comparison to ionic bonds. So with ionic bonds, when we had for example, a positive ion, the electrostatic attraction towards negative ions is in all directions. Okay, so this positive ion will attract negative ions in all directions. Okay. Whereas when we're looking at a covalent bond, this is what we call localized attraction. Okay, so over here, so where I've got the H is actually where the nucleus is. The nucleus, that region there, is positive. Same with this region over here, the nucleus of this atom is positive as well. If we then look at where the shared pair of electrons are, this region over here is negative. Okay, so when it comes to a covalent bond, the attraction is only between the shared pair of electrons here and this nucleus, and the shared pair of electrons here and this nucleus here. So we call this a localized bond. The electrostatic attraction is only in one direction. Let's just do some more examples. So let's now have a look at H2O, so our water molecule. So we've got 1 oxygen and 2 hydrogens. I'm only going to show the outer electrons over here. So oxygen starts off with, because it's group 6, it has 6 outer electrons. Okay, and hydrogen, I'm going to use crosses for these, has 1 electron in the outer shell. Okay, when these overlap, remember, all atoms want to have a full outer shell of electrons, or you can say they want to achieve the configuration of the nearest noble gas. So when these overlap, our oxygen is going to overlap with this hydrogen here, and it's going to overlap with this hydrogen over here. If I draw in all the electrons, as you can see, this oxygen here now has 1, 2, 3, 4, 5, 6, 7, 8 electrons, and this hydrogen here and this hydrogen here both have 2 electrons. So they've achieved their noble gas configuration, or they've achieved their full outer shell of electrons. If I want to show the displayed formula for this, it is oxygen, 1 bond to that hydrogen, 1 bond to that hydrogen there. We also show the lone pair of electrons here. So as you can see, these electrons here are not bonded to anything. Okay, so we call these lone pairs of electrons. So this is 1 lone pair. And this one here is another lone pair. And when it comes to displayed formula, we should technically show those lone pairs as well. So the oxygen has 1 lone pair there and 1 lone pair here. So as you can see, it's got 2 pairs, it's 2 lone pairs of electrons. Let's now have a look at another one. So I'm now going to go for ammonia, which is our NH3. So nitrogen has, it's in group 5, so it has 5 outer electrons. Okay, hydrogen, as we know, has 1 electron. So as you can see, for this nitrogen to have a full outer shell, it's going to bond with 3 hydrogens. So it's going to bond with 1 here. Hydrogen's going to share its electron there. Like so. Okay, if we now look at our nitrogen, it now has 1, 2, 3, 4, 5, 6, 7, 8 outer electrons, and therefore it has a full shell. It's happy now, and each hydrogen now has 2 outer electrons, and therefore it is now happy. Okay, so this is our nitrogen molecule, not our nitrogen molecule, this is our ammonia molecule, and as we can see, so nitrogen has 1 bond with 1 hydrogen there, another one here, another one here, and it also has this lone pair of electrons here, which we can draw in there. Right, just one more we're going to look at is our methane. So methane has 4 hydrogens and 1 carbon. So carbon is in group 4, so it has 4 outer electrons. And you may have guessed it, it's going to therefore form bonds with 4 hydrogens like this. And this is how it gets a full outer shell. So carbon now has 1, 2, 3, 4, 5, 6, 7, 8 outer electrons, and therefore it's happy. Each hydrogen now has 2. So for the displayed formula for methane, it's simply this. That carbon there doesn't have any lone pair of electrons. Okay. What you may also notice is each element that we've discussed in this always forms the same number of bonds, usually, okay? So hydrogen will always form one bond. So the number of bonds that hydrogen will always form is just one, okay? And every one that we've looked at, hydrogen just forms one bond. Carbon in this example, and most examples, carbon always forms 4 bonds because it needs to gain 4 electrons to become a full outer shell. Oxygen, because it's group 6, it needs to gain 2 electrons, and therefore oxygen will always form 2 bonds. And nitrogen, because it's group 5, wants to gain 3 electrons, so nitrogen tends to form 3 covalent bonds. Okay, there are exceptions to these, but most of the time these are the number of covalent bonds each of these elements will form.